Hello all, we are going to start a new chapter, chapter 7, flow past immersed bodies. So if you remember in chapter 6, we studied flow in pipes and ducts. So that was internal flow, and this chapter deals with external flow. So in nature and technology, especially for technological applications that we are concerned about, there are many, devices and cases in which a body, an object, an aircraft is exposed to an external stream of a flow, usually air and water. So for instance, what you see here, you see a bridge which is exposed to wind. We may want to know, definitely bridge designers want to know the drag forces or forces acting on a bridge. Also, what you see here, the aircraft, we want to basically uh, calculate the lift force, the drag force, and as a result design the engines in order to be able to provide, what is needed. So that's the motivation behind this kind of external flow with a wide range of applications. So one of the most basic types of external flows is flow over a flat plate. So here what you see on the top is a flat plate in the form of a wedge with a sharp edge, and we see a low Reynolds number flow, low velocity or generally low Reynolds number flow. At the bottom, you see that the Reynolds number has increased substantially to 10 to the 7 versus only 10. And we see a big difference in the shape of the basically velocity and pressure field that are formed around the plate. So if the Reynolds number, so let me read through this. So if the Reynolds number, which is again in this case, so let's define the Reynolds number. So Reynolds number in the case of a tube or pipe was rho density of the fluid, v like the velocity, the average velocity, d the diameter of the pipe divided by mu the viscosity of the fluid. So in this case the Reynolds number is defined in the same way, except that instead of d, the diameter, there is no diameter of the pipe here. Instead we do have, for instance, the length of the tube. So the length of the tube L is the characteristic length for the Reynolds number. So Reynolds number is defined as UL over nu, and nu is simply viscosity over density, the the kinematic viscosity, mu. nu. So mu is dynamic viscosity and nu is kinematic viscosity. So if the Reynolds number is low, the viscous region is very broad. So what do we mean by viscous region? So let's say here you do have a uniform flow approaching this flat plate. So in the uniform flow, there is no viscous effects because there is no velocity gradients. So therefore the flow is defined simply as velocity u, a constant. It's a very simple flow. Everything is known in that flow. But as soon as it approaches the flat plate, because on the surface of the flat plate the velocity is zero, no stick boundary condition, so the flow velocity is zero on the surface of the plate. So the viscous effects become present, emerge. The viscous effects emerge. Now the question is that how far the viscous effects are present in the flow. So here is the discussion. So the viscous region is very broad if the Reynolds number is low and extends far ahead and to the sides of the plate. There is no existing simple theory for external flow analysis as Reynolds numbers from 1 to about 1000. So if the Reynolds number is small, less than 1000, the viscous effect that you see shown by this dashed line is very broad. So essentially outside this dashed line you have constant velocity u, and then inside of it you do have a velocity profile as shown here. However, theoretically it is not easy to analyze it because the viscous region is sort of unknown and it is difficult to analyze. What it means it is difficult to simplify the governing equations, which are the Navier-Stokes equations. So it doesn't mean that this kind of problems have no solution or cannot be addressed or dealt with. It means that there is more work is needed. So for instance, the equations should be solved numerically for these cases. On the other hand, so for most applications, the Reynolds number is actually high. So at a high Reynolds number flow, the viscous layers, either laminar or turbulent, are very thin. So if the Reynolds number is high, then it's like a high velocity flow approaches the plate, and then only very near the surface, the viscous effects are present. Outside of this layer, so this layer is called boundary layer. This thin layer, which is at the beginning laminar and then becomes turbulent, depending on the length of the plate. This boundary layer is very thin, so inside of the boundary layer we have a viscous region. Viscosity is important, so outside of the boundary layer we do have like a uniform flow if the velocity far from the plate is uniform. So we will have a uniform flow far from the plate, on the above, below, and before the plate. So we define the boundary layer thickness, so this thickness of the boundary layer, as the locus of points where the velocity u parallel to the plate reaches 99% of the external flow velocity. So as you see here, we can think of a velocity gradient. So on the surface the velocity is 0, it increases, and eventually it should reach the velocity of the free stream, which is capital U. So, but this is could be a very gradual process, especially far from the plate. So we just say that when the velocity away from the horizontal velocity in the direction of the plate becomes 99% of the velocity of the free stream, we have reached the edge of the boundary layer. So it means that below that we are in the boundary layer, viscous effects are important. Above that, the viscous effects are not important. It's just like we have a uniform flow. So we will talk about this in more detail later, but for now, this equation gives the ratio of delta over x. Delta is the thickness, delta is the thickness of the boundary layer at any given x. So let's say at this point, x is measured from the beginning of the plate, the leading edge, and it's measured from the leading edge at any x. What's the thickness of the boundary layer? That we show it by delta. So this delta, the thickness, divided by x, so non-dimensionalized with respect to x, can be found by this equation. So for laminar flow, like Reynolds between 10 to the 3, 1000 and 10 to the 6, 1 million, Reynolds delta over x is obtained from this equation. 5 over Reynolds x to the power of 1/2. In the case of a laminar flow, Reynolds greater than 10 to the 6, the thickness is obtained from a different equation. So it is 0.16 divided by Reynolds to the power of 1/7. So we will talk about how to find these relationships later in this chapter. So flat plate was one example. Another important example is flow over a blunt body. So a blunt body, for instance, a sphere, which is a three-dimensional or an axisymmetric two-dimensional flow, and also a cylinder. So this could be, for instance, the cross-sectional area of a cylinder or a sphere. So if there is a flow, for instance, with a Reynolds number of 10 to the 5, you may want to imagine to see the shape of the streamlines, how the flow passes over this cylinder or a sphere. So you may envision it as what you see here in the top figure, a very nice and symmetric streamline. However, in reality, and particularly for this case, because the Reynolds number is large, what will happen is different. So what will happen is that the streamlines will separate from the surface of this sphere or cylinder and create a chaotic motion at the back or downstream of this blunt body. So this is called the wake. So we see circulations and vorticity and a kind of complex behavior rather than just one symmetric streamline behavior that you see on the top. So this can be very important because this can have very important consequences when we design objects that have this kind of shape. It can be from like ships, submarines, aircrafts, and so on, because assuming that, for instance, the flow behaves like what you see on the top, will result in wrong calculations and wrong assumptions and wrong design. I should also mention that this is for Reynolds very kind of large, 10 to the 5. However, if the Reynolds number here is, for instance, Reynolds very small, equal to 1 or 10, for Reynolds number, very small Reynolds numbers like 1 or 10, this schematic could be correct, because for small Reynolds numbers, the streamlines actually follow the surface, the boundary of the body. So this is called small Reynolds number problems are called Stokes flow or creeping flow. So, but what we are looking at here is for a large Reynolds number. All right, so let's do a quick example based on the equation 7.1 to see how these things work, to get a sense of these numbers. So we have a long, thin flat plate placed parallel to a 20 feet per second stream of water at 68 degrees F. At what distance x from the leading edge will the boundary layer thickness be 1 inch? So first of all, don't worry about the units. So we will stick to the SI units, but here is just an example. Unfortunately, I only had this version to show it to you. So we do have a thin flat plate, and we know that the boundary layer develops over this flat plate. And this is x, the distance from the leading edge, and this is delta, the thickness of the boundary layer. So this x is measured with respect to this point, the leading edge. So for a flow, let's say a free stream approaches this flow, and the velocity of the free stream is uniform at 20 feet per second. So we want to see at what length, at what x, delta becomes 1 inch. Is X like 1 inch? Is it 10 inches? Or just get a sense. All right, so for now we use equation 7.1 for delta over X. And first, well, we don't know whether the flow, well, the thing is that the flow at a small x's is laminar, and as x increases, it may become eventually turbulent. But to do this problem, first we assume that the flow is laminar when delta becomes 1 inch, and if we calculate the Reynolds number and see that it's very large in the turbulent region, then we would need to go back and use the correct formula. So this delta over x is for the laminar flow, 5 over Reynolds to the power of 1/2. So delta over x, it's non-dimensional. So we put 1 inch, convert it to feet, 1 over 12. X is unknown. And then 5 divided by the Reynolds number for, this is for what's the fluid? It's water. So we just go ahead and read the properties of water in order to calculate the Reynolds number. For Reynolds number, we do need the viscosity and also the density. So if we calculate it, we see that x equal to 513 feet, 513 feet. So it means that after, when x reaches 500 feet, delta becomes just 1 inch. So it may be correct or not, but we need to double check to make sure that this is actually a laminar flow at x equal to this value. So if we calculate the Reynolds number at this x, 513 feet, we see that Reynolds number becomes 9.5 times 10 to the 8. This is much larger than 10 to the 6. So actually the flow is turbulent. So it means that we have used the wrong equation, because the equations that we used to estimate delta was based on a laminar flow. So now we go back and use the other equation, which is applicable to turbulent flows. So in this case, the coefficient is different, the power of Reynolds is different. Same procedure for delta equal to 1 inch. Calculate Reynolds number. Now raise it to the power of 117. Reynolds number is the same as before, but now it's raised to a much smaller power, so makes the denominator larger. Okay, so based on this, if we solve for x becomes 5.17 feet. So if we go ahead and based on this x calculate the Reynolds number, so based on this x calculate the Reynolds number, so we see that Reynolds number becomes 9.6 times 10 to the 6. It's greater than 10 to the 6. So it is Reynolds, it is a turbulent flow. So we have used the correct formula to estimate delta. So you see that after 5 feet, or about 5 times 12, about 60 inches. So once x becomes 60 inches, delta approximately becomes 1 inch. So you can get a sense of, how thin this boundary layer is. So the ratio of the boundary layer thickness to the length is 1 over 60. So here we used the transition between, here we said that if Reynolds number is greater than 10 to the 6, then it's turbulent flow. Later we will see a more accurate number similar to the case of the internal flows, which was like 2,300. In this case, we also define a transition Reynolds number. For now, you see that we have used 10 to the 6. Below 10 to the 6, laminar flow. Larger than 10 to the 6, turbulent flow. So, okay, so let's see more details and definitions about a boundary layer. So assume that this is a flat plate and a uniform flow is approaching the leading edge of the flat plate. So at the leading edge, the velocity profile is uniform. So when the fluid comes in contact with the plate, on the surface of the plate, the velocity is 0. And then the velocity gradually increases and until it finally becomes equal to the velocity of the free stream, u again. So by definition, when the velocity, this lowercase u, becomes equal to 99% of, so when this lowercase u becomes equal to 99, so lack of, becomes equal to 99% of, so of this capital U. So when the at a given x, when the velocity, the horizontal velocity adjacent to the plate becomes 99% of the uniform velocity, then we say that, oh, okay, stop, this is the edge of the boundary layer. So we can find many of these points at a different x. This delta, this 99% would be different. So when we connect all of these points together, we get the edge of the boundary layer. So inside the area between the space or the region between the plate and the boundary layer edge is viscous flow. Viscosity is important. Outside of it, which is called the outer region, viscosity effects are negligible because velocity does not change much. So velocity gradients are kind of absent, therefore the shear force is absent in the outer region. Another thing is that, so here you see that because of the presence of this boundary layer, the viscous effects, there is a shear stress force per unit area acting on the flat plate. So this causes like a drag force. So if we want to keep this plate in place, we need to apply an opposite force, for instance, a force, the drag force, in order to keep it in place when it's exposed to a free stream. Okay, so another example, are low speed, small scale air and water boundary layers really thin? So air, we consider air and water boundary layers to see how thick or thin they are. Consider flow at u 1 feet per second past a flat plate which is 1 feet long. Compute the boundary layer thickness at the trailing edge. So trailing edge means the other end of the plate. So this is a kind of short plate, is just 1 inch, 1 feet long. So we want to find the thickness of the boundary layer for water and air. So first let's do it for air. The kinematic viscosity of air is found from the table. Then Reynolds number for this condition, 1 feet per second. And at x equal to 1 feet, this is the Reynolds number. This is very small. It's still greater than 1000, so the boundary layer approximation is fine, but we do have a laminar flow. So we go ahead and use the laminar flow equation for delta over x, 5 over square root of Reynolds, and it is equal to 0.06 or 6 centimeter, or in terms of inches, at x equal to 1 feet, delta is 0.076. So it's not to scale. It means that in reality the thickness would be something like this if we want to draw it in to scale. So yes, it is quite thin, so less than 1 inch at a distance of 12 inches from the beginning, and this was for a laminar flow and for air. If we do have water instead of air, we use water, the properties will be different. So the kinematic viscosity and then Reynolds number, the kinematic viscosity of water is much smaller than kinematic viscosity of air. So Reynolds number of water is larger than that of air. 92,000, it is still less than 10 to the 6. So it's laminar flow, and we use the same correlation for delta over x, and this time delta becomes 0.2 inch. So after 1 feet or 12 inches, delta becomes only 0.2 inches, so much thinner than air. So the boundary layer associated with water is much smaller than the boundary layer thickness associated with air. So even the velocities, even at such low velocities, 1 feet per second is a very low velocity. So in reality, in most cases, 1 feet per second is like a breeze. So it's a very low velocity air or water stream. Even in this case, the Reynolds number is larger than 1000, as we see in both cases, and the thickness is really much smaller than the length of the plate. Unless let's say you said, okay, how about this? If we consider a plate which is just 1 inch long. So if this is the case, then you really cannot say that you do have a boundary layer situation here, because the plate is so short that the assumption of the boundary layer is not valid. So boundary layer, what's the assumption behind boundary layer? It has to be thin compared to the length of the plate. This is equivalent to saying that Reynolds number should be large. So if for a plate the Reynolds number is at least, for instance, larger than about 1000 or 10 to the 3. If Reynolds number for a very short plate, the Reynolds number becomes very small, because Reynolds number is a function of x. So if you use a very short plate, then this boundary layer concept does not work. And in reality, we really don't, in most cases, in most technological applications, the boundary layer approximation works. And I should mention that this boundary layer theory, it can be like a complete course, but usually it's taught in the graduate level, and if it can be, a lot can be taught and told about this boundary layer theory. Here we just talk about the most essential parts, definitions, some applications, useful equations for design purposes. So we are not going to go into the details. There is a lot behind it. It's highly mathematical, highly theoretical. So we just scratch the surface of the boundary layer theory. Okay, so speaking of details of boundary layer theory, so even though we want to be very practical here, but I like to show you the equations behind this boundary layer. So we said that in the boundary layer, we do have viscous flow. Outside of it, it's like, well, viscous effects are not present, we call it potential flow, or inviscid flow outside, or irrotational flow outside of the boundary layer. So let's see what are the equations, the governing equations. First, consider a two-dimensional problem, meaning that the plate that you see here has an infinite length proportional to the screen. So this only becomes a two-dimensional problem. We just look at the cross-sectional area and we call it x and y. So in x direction is in the direction of the plate and y direction is perpendicular to the plate. So this is the same picture or the same schematic that we had before. So this is our boundary layer. So what are the governing equations? So first, we do have the continuity equation or conservation of mass in two dimensions. This is del dot divergence of v equal to 0. So this is del dot v equal to 0. In two dimensions, it's equivalent to du dx plus dv dy in the partial form equal to 0. There is no z component. It's z component w. If you think of z component, w is equal to 0 because it's two-dimensional. The flow doesn't move in z direction. Then we do have the Navier-Stokes equation or momentum equations for a Newtonian fluid, neglecting g. So we do not consider the effect of gravity. So g is 0 or its effect is insignificant. So you see here g is not considered, gravity. So there is no gravity term here. On the left side of this equations, we do have the acceleration. So the first equation is in x direction, and you see that the velocities are u, lowercase u, the velocity in x direction, and in y direction, the velocities are v. So the first of these two is the momentum equation in x direction, the second one in y direction. Okay. So we do have the pressure gradient term. So on the left side, we do have the acceleration. On the right side, these are the forces that cause this acceleration. So one is the pressure gradient that causes acceleration, surface forces. Body forces are neglected. We do have only surface forces that cause acceleration. And then this one is the gradient of shear stress. So on this, so this force plus this force, F equal to ma. Everything is per unit volume. So it's like the second law of Newton or conservation of moment in x and y direction. Okay, so we had this in chapter 4. So these are the general equations that we have in this boundary layer where viscosity is important. Outside the boundary layer, the velocities really do not change. So the terms that you see in this parentheses will be 0. So outside the pressure also, for instance, for uniform flow, the pressure doesn't change. So outside of the boundary layer, we just have a very simple flow, like velocity is a constant. That's why we are not really concerned about outside of the boundary layer. Inside of the boundary layer is problematic because there is a complex relationship between velocity and pressure. However, the good news is that in the case of a boundary layer, we can go ahead and simplify these equations simplify these equations, and even come up with a solution which was obtained long time ago, I guess 100 years ago or so. So this lecture is becoming too long. Let me stop here, and then we will continue in part 2 of this lecture. But in part 2, we again will start from this slide, and then we will move it forward. All right, thank you for watching, and see you soon again.